Hello and welcome to Reigate Maths. This is a video focusing on the probability section of the first year A-level statistics from the Edexcel syllabus. My name's Simon, and in this video we're going to be focusing on the cumulative binomial distribution. This video extends the idea on a previous video focusing on the introduction to binomial distribution, so if you haven't watched that one yet or just need a refresher, I'd advise going to watch that one first. So what are we talking about when we talk about cumulative binomial distributions? So when we were looking at in the previous video, we were looking at this type of thing, an exact number of successes. What makes it cumulative is when we start doing inequalities with it. So it could be any one of these four possibilities. And that's what we are looking at with the cumulative binomial distribution. The nice thing is that our calculator will do this for us. So we have to do very little manipulation to figure things out. The key thing, though, is the calculator can only cope with this one. If it's any one of these three, we've got to do some rearranging first before we then use the calculator. So we're going to crack on straight away with some examples to show you what's going on. So this is the example we're going to start with. 25% of students travel by train. In a group of 40 students, find the probability that no more than 7 travel by train. So we're going to start off by writing our distribution. I know we should explain what x is, but in terms of getting the ball rolling with these, I want to go through the maths of this itself. So we know x is distributed binomially. We have 40 successes, and the chance of success is 1/4. So, what probability are we working out? Well, we want no more than 7 travel by train. So 7 or fewer travel by train. Now, because this is a less than or equal to, we can use the calculator straight away. So the way we do that is, we still need to, like in the previous video, we need to press menu, then 7 to go for distribution. Now we do not use binomial PD for this. We need to scroll down until we see binomial CD for cumulative. We choose that, and again we choose variable. In this case, x is 7, n is 40, and p is 0.25. So our calculator for binomial CD gives us exactly this, which we just write down. So we get 0.182. So as long as it's less than or equal to, we can just do this straight away. So again, menu, 7, scroll down, binomial CD. Variable, type in the information. When we look at our part B, we're going to have to do some other bits first. So here's our next example. In a group of 50 students, find the probability that at least 18 travel by train. So we now have changed n, so we have a new distribution. And at least 18, it's probably that x is bigger than or equal to 18. Now it's an inequality, so we're still going to be using binomial CD, but it's not a less than or equal to, which means we've got to do some rearranging first. And the key thing with this is, like with the table previously, think about your number of outcomes. So we could have 0 outcomes, 1, up to 17, 18, 19, and then up to 49, 50. Now I don't write them all out because there's 51 different outcomes, including the 0, and that's a lot. Because we're only interested in what's happening around this one. So let's have a look-see. So we want 18, 19. Those are the outcomes that we're interested in. So we want this lot. We know that all of the possible outcomes add up to 1. So if we worry about this bunch, we can work out this one. The way we describe this lot is 17 or fewer. So x is less than or equal to 17. So to get this bunch, it's going to be the whole thing minus this probability. And this is the one that we can do on our calculator. So now we go back to our binomial CD. X is now 17 and n is now 50. So this is the probability that x is less than or equal to 17. And then we just do 1 minus that. And that's how we do greater than or equal to. So here's the final example for this set, and this is the type that students typically find very difficult. So we've got in a group of 50 students, find the probability that at least 20 but no more than 30 travel by train. So this is not just a single-ended probability or a single-ended inequality, this has 2 limits. So we want the probability that x is at least 20 but no more than 30. Now we have a less than or equal to here, which means sort of bits of it we can do using our calculator, but this is the problem. We need to be able to split this into 2 inequalities, both of which are less than or equal to's. So again, like before, let's have a look at our possible outcomes, and I'm just going to do it a little bit of a ways underneath. So we have 0, 1, up to 19, 20, 21, then up to 29, 30, 31, and then 49, 50. So which ones do we want? We want 20 up to 30. Now, if we take kind of this top end, because this is not a problem. This is already a less than or equal to. We can still do things with our calculators. So ignoring just that, this whole section is that bit. So this is the probability that x is less than or equal to 30. Now we only want this middle bit. We can currently work out easily this whole section. We only want this bit. So if we remove this section here, we're just left with what we want. How do we describe this section using a less than or equal to? It's less than or equal to 19. So this double-ended inequality is going to be the same as p of x is less than or equal to 30 minus p of x is less than or equal to 19. Now, individually, you've got to work out each of those on your calculator. Now, if you It's generally quicker to do variable twice, but if you want, you can use the list function. So what the list function does is it allows you to have a bunch of different x values in one go. So we're interested in x is 30 and x is 19. So if you press equals to type them both in, and then equals again to say I'm done typing in x values, now we can type in n and p. Oops. 50 and 0.25. And we can see the calculator then tells us each of those two probabilities. Now this one is massive, or it's very, very close to 1. Now, the reason I went back there is this kind of surprised me, so I was just checking I'd typed it in right, and that's always something you should do if you think that the answer you're writing down is a little bit off. So we've got 0.9999999. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 654 minus 0.98608233914. You probably don't need to write everything down, but just to a few more decimal places than your final answer is fine. So we've got 0.9999. We'll do it to 4 decimal places. Well, to 4 decimal places, this is 1. 9861. Which give us 0.0139. And that's our probability there. Now, the thing with this is you can start then having strict inequalities, which also then make this a little bit stranger. So you need to think about this in this way. Kind of, as long as you can pay attention to the number of successes and use this kind of idea, it makes it very easy to work out these probabilities. This is the final example we're going to look at for this video. I'd like you to pause and have a go once we've talked through it, and then we'll come back and we'll have a go. So, a spinner is designed, the probability it lands on red is 0.3. Jane has 12 spins, and we want to find the probability that Jane obtains A, no more than 2 reds, and B, at least 5 reds. So that's not very different from what we've been doing. Part C, Jane decides to use the spinner for a competition. The probability of winning a prize must be less than 5%. Each person will have 12 spins. Find the number of reds needed to win a prize. That is a more difficult bit, so if you pause, have a go at the whole question, see if you can come up with an answer to part C, and then we'll go through it. So, generally, like before, we need to identify what our random variable is. Now, you could use X, you could use R for red if you particularly wanted to, but traditionally we use X or Y. So XB, the event, the spinner lands on red. So X is distributed binomially. We've got 12 trials and probability of success 0.3. Part A, we want no more than 2 reds. We're not told to use the formula, so we just use our calculator. Menu 7 down to CD for the inequality. It's a less than or equal to, so we're fine. We don't have to play around with it at all. Variable. We have 2 successes, 12 trials, and probability of success 0.3. Hit equals, and that's our answer. 0.253. For part B, we want the probability that we get at least 5 reds. Again, we want to use our calculator because it's an inequality, but it's greater than or equal to, so we can't do that. So the kind of general rule of thumb, if it's greater than, it's going to be 1 minus. If it's less than, it's not. So if it's greater than or equal to, it's 1 minus, and then drop this number by 1. If it's strictly greater, you keep the number the same. So if this was strictly greater than 5, it'd be 1 minus probability that x is less than or equal to 5. If this is strict, you don't do 1 minus, you just drop the number by 1. So if its probability that x is less than 2, that's the same as less than or equal to 1. That's kind of your rule of thumb for those using your calculators. So we're going to do 1 minus 0.7237. Now, I know we typically give our answer to 3 significant figures, but give all working to 4 just in case. Doing 1 minus our answer, we get 0.276. So that is the probability that x is greater than or equal to 5. Now for part C. So the way we can approach this is we can think, okay, we want someone who gets some number of reds or more to be less than 5%. So this value of r needs to be less than 0.05. Now our calculator can't cope with greater than or equal to's, so we need to rearrange it to a less than or equal to. And we've already seen how we do that. So here we had greater than or equal to 5. We made it 1 minus less than or equal to 4. So we can change this to less than or equal to r minus 1. Rearranging, we get that we need this value of this probability of r being less than or equal to r minus 1 to be greater than 0.95. Okay, just rearranging. So now what we can do is we can use our calculator. So we're still doing binomial CD because it's an inequality, but now we can look at our list. We want the values in our list to be, or we want to find the ones that are bigger than 0.95. So what we can do is we can go, okay, well, we could just type in 0 through to 12, but that's pointless. We know that the probability of getting less than or equal to 12 will be 1. And the probability of getting less than or equal to 0 is going to be very, very small. So we can be clever with it. We can start by considering the expected number of outcomes, which is what you get when you times these two numbers together. So 12 times 0.3, the expected number of outcomes is going to be 3.6. So 4-ish. So we'll start with trying 3, 4, 5, and 6, because why not? So it's going to be around there somewhere. If this doesn't work, we can just add more numbers to our table. We've still got n as 12 and p as 0.3. So now we can see, okay, in our table, the probability of x being less than or equal to 3 is 0.493. Less than or equal to 4 is 724. Less than or equal to 5 is 0.882. And then we get this one. The probability that x is less than or equal to 6 being 0.961, which is bigger than the number that we wanted. So, we know from the table on the calculator that the probability that x is less than or equal to 5 is 0.8821. Which is less than 0.95. This is important to say, this is the one that we ignore. This is the biggest value of x that we can ignore. And we know this probability of x is less than or equal to 6 gives us the value that we want. So therefore, r minus 1 is 6. Remember, r minus 1. So r is 7. Which means that 7 reds are needed to win the prize. What we have done here is the same maths as what we will look at in future videos, something called hypothesis testing. So later on, this is the same maths for finding the critical region of a hypothesis test. So when we get to that, you know what to look for. This is genuinely as hard as the binomial distribution questions can get. So if you can follow this, very well done. Future videos will be looking at this idea of hypothesis testing, and then next year that idea of hypothesis testing comes back a couple of times. Thank you for watching.